Welcome to this session where we are going to have an introduction about MEMS technologies. So this introduction will give you an idea the coverage, so how much we can explore the basics followed by how to design a particular MEMS device. We can design, model, analyze, validate the entire results. So good morning, we can start now. So here, the sessions are organized in such a way where the crystal structure, its orientation, the crystal defects, followed by so what all the impurities we have with respect to silicon. Silicon is going to be the primary material. So based on the properties of this silicon material, we can go for a lot of devices, followed by gallium arsenide. So this gallium arsenide is also high conductivity material. Mobility is also good, where high-speed devices can be designed. And that will be useful for the ultra design and polymer, followed by different types of polymer. We have PMMA, PDNS, LCP, SU8. These are the different polymers which are used in MEMS design. Because nowadays polymers are replacing the natural materials like silicon. Silicon, even though it is available in abundance, these polymers also play a vital role in building a design. Parylene is one of the important polymers where it is used for the nano as well as followed by the nanostructure design, titanium dioxide. A lot of sensors we can see with the parylene, PMMA, polyamides, silver, synthetic amorphous silicon iron oxide, and a lot of nanotubes design, carbon, fullerness, everything we can design. We can explore the properties and we can go for the design. So how these crystal orientations will be. So that is explored in this particular section. So here how we can take this silicon material and we can go for the crystal design. The crystal is going to have different lattice, the plane. So edges. So how it would be in different planes like 100, 010, 110. So here we explore in terms of x, y, z axis. So this particular phenomena makes it to build lot of designs. So now we can explore into the lattice structure, the crystal, where it is used, the silicon crystal. So what we are speaking about is a silicon crystal. So the electrons in the outer orbit and we have this inner shell. So valence electrons are going to be 4. And here it is a bonding structure which is established. It's a covalent bond where the atoms are going to have a sharing phenomena by means of having sharing electrons. So valence shell is going to be a complete structure. This results in solid that is electrically stable and it's going to have a poor conduction also sometimes. The outer energy shell has 4 electrons in space for 4 more where it can accommodate. So now, so this is going to be the sharing phenomena. So where we can see this bonding now for this particular. Now the orientation. So we can have this orientation structure. So whenever it is exposed to wafer surface, the middle images highlight two different planes within the crystal silicon. So thereby two different directions we can have. So you can see this middle structure. So with respect to this middle structure, You can just go with the highlighter. The middle structure. So with this middle structure, it has been classified into two types. So how it looks in different directions, looking at the same crystal, even though we are just looking at the same crystal, so it's going to be with different directions. So that is orientation part, where same distance between the unit cells are going to be maintained and the orientation of each unit. So here we can have this different plane structure which is going to be of use, and the properties of silicon is going to be explored. So now this silicon property, where it is going to have a silicon monocrystalline wafer, the properties are going to be with respect to the conductivity, which is an electric, and reaction potential, and ability for etching, where potassium hydroxide is dependent on its orientation, and different bonding with respect to the mechanical properties, how it is going to bend, and it's going to depend on the orientation, which is based on the applied stress. So now look into this crystal plane, where each plane is going to be a unique one. So Miller index is going to be a popular one, where it's going to identify the crystal planes of the crystal. So Miller indices, where we have this XYZ plot, which is in the Cartesian coordinate system with respect to the vectors of XYZ. So we'll be having this plane structure. So x-axis vector, if you take, it is x100, and y-axis it is 010, and z-axis it is 001. So this is going to be the typical structure. In alternate vectors, how we can define for all these, and with respect to these planes, so we can have different orientations where it starts. It's a three-axis coordinate, so we can have different combinations of three factorial terms. So different forms we can have. So now look into a particular plane where it is 100. So the shaded region which shows the 100. So you can have the shades, and with respect to that we can analyze. So this is your 100 plane. You can go with a different color so that it will here. So this is a structure. So which part and shading, no? So this is going to be your 100 plane. X value is 1, Y value is 0, Z value is also 0. So I think this plane you can. So now properties which are going to be defined. Microsystems and MEMS design. It goes with the crystal orientation, the crystal planes which we are considering, the structures with the defined edges, length, width, and thickness. So certain electrical property which would be taken for the resistance calculation, mechanical it is for the bulk property, and optical for the refraction index. And these properties are set with respect to different crystal orientation. So how to make a silicon wafer? This is a very primitive part where propulsive method is going to be the silicon manufacturing process. The bowl is going to be manufactured. So as shown in the figure, so this C is a process. In short, we call it as a propulsive with the C is a method. So here, this molten silica is nothing. So many of you will be wondering, like it's like a just a sand. So this sand, it is available in the form of a molten part, and it is taken into a crucible which is heated 1200 degrees Celsius in a furnace, and from that we have this pulling effect which we call it as a seed crystal. So this seed crystal in a molten form, it is pulled over by means of this pulling action between back and forth. You can see this, and by means of this puller, we will get a cylindrical ingot. We call it as a silicon ingot. Since the structure is going to be in a cylindrical form, we call it as silicon cylindrical ball. So you can see this particular action where it is going to be pulled from the seed crystal silicon. So in the form of a wafer, how we can organize. So this ingot, it is in the bowl shape. So this bowl is nothing, it's a cylindrical bowl. So many of you would wonder like how this bowl is going to be manufactured. So it's a very simple process, which is a very conventional design which is being carried out, and it has been named after the scientist of Procral. He has done this ingot bowl, and to the industrial standard we can manufacture these bowls. So the standard manufacturing process is going to get you an ingot in a particular dimension of 100 mm cross 100 mm by 100 mm, or it can be between 150 up to 200 mm, the length, width, as well as the thickness, the height and the thickness. So this LBH. So industry is going to prefer a bowl which is of 150 mm by 150 mm by 150 mm. And this crystal orientation is going to be determined with respect to a pure silicon crystal material, and it's going to have a molten silicon, a lower seed crystal ingot is going to be obtained, and the large diameter of the crystal ingot, how it is formed, and from that the alignment of atoms is going to be happening in the alignment of seed crystal, which is going to have a melting phenomenon. The orientation is going to be there. The wafers have been cut from this crystal in order to maintain this particular orientation. So now how the third 3D geometry structures of a unit cell. So the basic forms are going to be simple cubic, face-centered cubic, and body-centered cubic. So what's the difference between face-centered and body-centered is that it's going to be, so you have seen a cube. The cube is going to have 6 faces. So with respect to the faces, the center is going to be determined. So then it's going to be a face centered. And if you see the body diagonal of it, with respect to that, the orientation and the center point is going to be located, then it is a body centered cubic. Both are of use when you go for a particular design. And simple cubic structure is going to explain you how different planes are organized, and from that how the characteristic is going to be determined. So now if you are taking this face centered, and how the shift is going to be along the diagonal. So if you take a diamond crystal structure, diamond is also a cubic lattice, where silicon is also a cubic lattice. So you can see this diamond cubic, and where the atoms are going to have sharing. So sharing is nothing, from the covalent bond itself we have the sharing phenomena, and the lattice parameter H length, if it is a 0.5 nanometer, nearest neighbor distance is going to be 0.235. So how well we are shifting these, and accordingly the lattice parameter, the H length, are going to be determined. So you can see it's an equidistance. So for a cube, it's going to be an equidistant plane. So you can see this face centered also. If you connect the face center, so how to go with this particular structure? Many of you are getting confused with respect to this. First, you need to draw on all the 6 faces the center point you need to look and try to join all the center points. If you are joining these center points, you'll be getting an equidistance. That is going to be the neighbor distance calculation. We have taken the H length to be 0.5, and exactly by 2 of it if you take, it's going to be the neighbor distance. I think this helps you to understand the concept with respect to face-centered cubic sheets. Now coming to the calculation part, so we know what is a corner face and what is inside. So with respect to that, the 8 corners, so if you take one particular unit cell, then it is 1 by 8 of the unit. 6 faces are going to be there in a cube, thereby 1 by 2 atoms of the unit cell. 4 full atoms. Thereby the cell volume is going to be captured 0.5 nm the whole cube, and in terms of centimeter cube we can have a conversion in cell volume can be up. And density of silicon atoms, so it is represented in terms of the corner. So here 8 atoms are going to be there at the corner divided by the cell volume which we have calculated here. With respect to that, it is 5 into 10 power 22 atoms per centimeter. So these concepts are very lagging with respect to students, because once they look into the structure, they're getting confused. So lower energy state, it's going to be the diamond lattice, and 4 electrons are shared between the neighbors, and this, it's like a covalent bond sharing which appears. So because this is a covalent bond structure, how silicon atom is surrounded by the remaining silicon atom, thereby it becomes a very stable atomic structure. Each atom appears to be in the balance. The outermost shell is going to be complete one. If it is a complete one, then a stable structure is going to be organized. So we'll be having this net effect of combining the crystal structure. So with respect to that, the lower energy state, higher energy state, where there is no gap, so all these are going to be identified with the conduction valence band, and a band gap is going to exist between the two bands, and a Fermi level is going to be established. So this we can go with the property of silicon material, and thereby the binding energies can also be found. And these are some of the basic definitions which you can go through. So it's a very basic one of amorphous and crystalline, how crystallography arrangement. It's an arrangement, Miller index. Indices, polycrystalline is one of the important property. A material which is there, which is used for a lot of applications, CMOS technology, everything. We have this polycrystalline as a metal, and unit cells are going to be there. These are the definitions which you can go through. Thank you for your patience in listening. We'll meet in the next lecture. Thank you.